Hi, I am Chandrasekhar Gupta and we are discussing programming concepts. Before talking about time complexity, let's go to a racetrack. Suppose you went to a race and the first person is with a bicycle, the second person is with a car, the third person is running on foot and they were running the same distance. Do you think it is going to be a fair race? No, right? That's just because each and everyone are running or utilizing their own resources and their capability is extremely different. In a similar way, when we are trying to run the same program on computers, different people are having different processors, different RAM size, different cache size and completely different technology. So, it will be completely unfair to compare the efficiency of a program based upon the time taken for its execution. What can we do? Can we compare it based upon the number of statements that has been written? It differs from program to program and it depends completely upon the programmer. So, they have defined a better way to calculate time complexity and let's have a look. Let's try to understand time complexity. It has best, worst and average cases which are denoted by big O, omega and theta respectively. To understand it further, let's try to take a graph and we'll try to interpret all these cases and all these notations from that graph. Consider this graph. I have used size of input and time taken for execution on different axes. Now, what is the relationship between the size of the input and time taken? Suppose, if you are performing an addition, if you want to add 3 numbers, it may take around 20 seconds. If you want to perform the addition for 5 numbers, it may take around 60 seconds. So, when you try to increase the size of the input, the time actually increases. Let's say we have taken a problem that, for example, if it is sorting, we are giving some numbers and this is the time taken 1, 2, 3 and so on. This is the rough estimation. For sorting 2 numbers, if the time has been at this point. For sorting 10 numbers, if the time was at this point and so on. So, the graph will be as such. This is the curve which represents the time taken for execution for our program and let's call it as f of n. Consider some other graph which is c into g of n and consider another graph which is k into l of n. We can even estimate f of n as the above graph or even as the below graph. So, for different problems, we'll be having different types of graphs, which is the value of f of n will be changing dramatically for each and every problem. But we have some fixed notations, let's say n, n square, n cube, log n and so on. These are some fixed numbers. So, we try to take our actual graph and then we link it to any one of the standard notations. If you have taken, let's say f of n is equal to 3n plus 4. If you have taken 4n, after a value let's say n naught is equal to 4, 4n will be always greater than 3n plus 4, right? So, 3n plus 4 can be estimated as 4n. Now, we are trying to increase the bound. We are trying to take a figure which is always greater than after a specific limit. This is, we are going or considering the worst case. And the worst case complexity can be represented with the help of big O notation. If you have taken a value of 2n, 3n will always be greater than 2n. So, if you try to write 3n with the help of 2n, let's say this is 2n. It can be represented with the help of omega notation. If you just see, big O represents the worst case. Even though the time taken is less, we are trying to increase or take a standard bound which is above, or we are going to consider it the worst level. But in the case of best case or omega, even though the time taken is more, we are trying to take a standard function which is much less than the time taken by our standard program. This is actually the best case. In this case, for this function 3n plus 4 can be written as order of g of n. G of n is 4n, so order of 4n or big omega of L of n which is 2n. It can be interpreted as order of n and omega of n respectively because we tend to ignore the constants when dealing with time complexity or space complexity. If your complexity turns out to be 4n, it can be treated as n. If your complexity turns out to be 10n, it can be treated out as n. This can be done as such because we can actually choose a CPU or a processor where this task will be divided between the 4 processors and can be completed in the time taken to perform n operations. Similarly, here we can use 10 processors at a time and we can complete it in the same time to perform n operations. So, if you have a constant work that has to be done, it is equivalent to order of 1. This holds in terms of time and space complexity as well. There is one more point that has to be remembered while we are dealing with complexities. Let's try to understand that. Consider a situation where complexity is termed as order of n square plus n. It can be interpreted as order of n square. This is because if you are going to buy a car and if you have also bought its cover, you will never specify the cost of the cover while you are telling it to someone else. Let's say you have bought car for 10 lakhs and you have bought cover for 500 rupees. If someone asks you what is the cost of the car, you will not tell him 10 lakh 500 rupees, right? You will just tell him 10 lakhs. So, when you are trying to specify a larger value, you tend to leave the value which is at the lower bound. Similarly, in the case when we are estimating time and space, we tend to ignore the lower bound. If you have order of n square plus n, it can be written as order of n square. If you have order of n cube plus n square, it can be written as order of n cube, and so on. We have understood that there are three notations: big O, omega and theta. We have already talked about big O and omega. Have you ever got a doubt why and when the theta has been used? Theta actually is used to represent average case. If big O and omega represents the same function, in the previous case when the function is 3n plus 4, it can be represented with the help of order of n and also with omega of n. When both of them are equal, we can represent it with theta of n, or just simply remember it is the average case. Let's try to estimate time complexity and how the time complexity will be calculated. Consider this example. Here I am trying to run a for loop from 0 to n. So, Gupta, this is the task that has to be performed. In the maximum or worst case, it will be performed n times. A task is fixed and it has to be repeated n times. That is the best case. Even the worst case is n times here. That also makes the average case to be n in this case. If you consider this example, the value of I is initially 1. And it is incrementing by 2 at every stage. Initially at the first time I value is 1 and this will be executed. So Gupta will be printed once. Now the I value is changed to 2. Again 2 is less than n. The condition is true. Gupta will be executed or printed again. Let's say the value of n to be 32. The I value is incremented again and the I value becomes 4. 4 is less than 32. Again it will be printed. And the I value will be incremented to 8. Again it will be printed. 16. Again it will be printed. Now the I value is 32. Now when the I value is 32, the condition fails and it tries to come out of the loop. If you just observe, it has been executed only 1, 2, 3, 4, 5 times. At this stage, the loop has not been entered and the output will be 5 times of this printing statement. Here the value of n is 32, our initial value is 1, we are incrementing it with 2 at every stage, or we are scaling it up with 2 at every stage. So initially the value is 1, 2, 4, 8, 16. So let's say after k stages, the value of I will be 2 power k. You just need to understand after k stages means it has completed k iterations. So it has entered the loop k times. 2 power k, it stops when this value is equal to 32. That is, k is equal to log 32 to the base 2, which is equal to 5 in this case. If we just observe, when the value is being multiplied or scaled up by a particular number, the complexity is becoming log n to that base. Here in this case it is 2. If you are multiplying with 3, you just try to work out, the complexity will turn out to be log n to the base 3. Let's try to solve some more examples with time complexity. Consider this. Initially the value of I is 0. The condition will be verified. Let's say n is equivalent to 3. So 0 is less than 3. The condition is true. It enters the inside for loop. And this loop is completely nested inside the for loop. The value of j is 0 and it will be executed k number of times. This we can get with the help of our practice. This loop, as it is incrementing by only 1 at every stage, we know that this will be executed k times. Initially, when the I value is 0, it enters the inside loop and it executes or prints the statement 3 times. The I value will be incremented by 1 and the inside loop will also be executed again k times. Similarly, I value will be 2, inside loop will be executed k times. Here, when the I value becomes 3, the condition fails and it comes out of the loop. if we just observe, the outer loop has executed n times. So, for each and every time, the inner loop has been executing k times. The total number of times the statement will be printed was order of nk. If this k is also equivalent to n, it becomes order of n square. You can just understand, if there is a nesting of loops, it actually multiplies the respective number of times. Now, instead of the loops being nested, suppose if you are having two loops separately, initially you are having a loop and then you are having another loop after that. You are having a for loop initially. After the execution of this for loop, you are trying to execute another for loop in the same function. This has to be executed followed by this. Then in this case, this will be executed n times and this will be executed k times. The complexity will be equivalent to order of n plus k. You will multiply the complexities in case whenever it is nested, or you will perform addition if it is performed separately. Let's try to understand recursive examples. Consider this example. You are trying to call this function recursively with the help of half the value of it. If you just observe the time taken for calling this function, let's say the formal argument is n, the time taken for completing n is equivalent to 2 times the time taken for n by 2. And also the time taken for doing the other work, which can be taken as constant. Let's say it is c. This is how a recursive equation can be formed from the recursive code. Let's try one more example. Consider this example. Here, the time taken for n is equivalent to time taken for n minus 1 plus some constant work. So, time taken for n is equivalent to time taken for n minus 1 plus some constant work. If I just substitute n minus 1 in place of n, then I'll be getting this equation. So, in the place of time taken for n minus 1, I can substitute the whole equation, which will be as such. Now, t of n is equal to t of n minus 2 plus constant, which is replaced in this position, plus constant. If you just observe, it is in the form of t of n is equal to t of n minus 2 plus 2c. So, if I have k here, then I will be having 2 into c or 2 into k here. Then I can modify this equation as such. T of n is equal to t of n minus k plus 2k. If you are not able to follow this, just try to replace n minus 1 again with n minus 1 or n with n minus 2. Then t of n minus 2 is equal to t of n minus 3 plus constant. Just try to substitute it in the place of t of n minus 2. And then it will actually become t of n is equal to t of n minus 3 plus 3c. So, it can be represented as t of n minus k plus k into constant. This will be c. We know that when the value of n is equivalent to 0, then this will not be executed and only the return statement or the constant work will be performed when the value of n is equal to 0. In all the other cases, the equation is as such. Let's try to take this final equation and we'll try to solve the complexity for this example. The final equation that has been obtained was t of n is equal to t of n minus k plus k into constant. We know that t of 0 is equivalent to constant work. So, I know the value of t of 0. If I substitute k is equal to n, then t of n is equal to t of 0 plus n into constant, where t of 0 can be replaced with a constant, n plus 1 is into constant. This is the total work or the total time that has been taken to complete the execution of this program. So, the complexity is order of n plus 1 into constant, which can be translated as order of n plus 1, as we know that order of constant is equivalent to order of 1. I can even modify it as order of n. Just try to remember the car and cover concept. This is how the time complexities are calculated.